Here's an interesting kinematics question which was given to ninth graders sitting the Romanian Physics National Olympiad back in 2018. So this is just problem 1A, part B. I'm gonna skip part A because part A of problem 1A is, in my opinion, not that interesting. If you do go over the paper as a way to prepare yourself, you should do part A as well, but I'm going to skip straight to part B. So if you have any questions that you'd like to see me go over from previous past Olympiads, or if you have any questions that are similar to those, let me know down in the comments. So let's read the question as usual, and then let's try to solve it. So we're dealing with two particles which are moving in the xy plane simultaneously, and they both start from point O here. And the first particle is moving to the right. Initially, it's moving to the right with an initial velocity of 4v0 and a constant acceleration of minus 4a, while the second particle moves along the y-axis with an initial velocity of 3v0 and a constant acceleration of plus 3a. So we have essentially two constants, I guess, which are v0 and a, and both velocities and accelerations, they are multiples of v0 and a respectively. So for part B, which is the only part that we're going to look at, it says determine the moment in time when the relative velocity is minimal, as well as the expression for the minimum relative velocity. Okay, so obviously for this we can just solve it using the basic equations of motion for the two particles that are accelerating. So what we can do is, or what I would do is, I would look at each particle individually, and I would try to come up with an equation for the velocity of that particle, because we just have to find the velocities, because then we have to find the relative velocity. So if this is point O, and then the initial velocity of particle, let's call it particle 1, I guess. So this is going to be particle 1 going along x and particle 2 going along y. Now particle 1 is initially having a velocity of 4v0, and it's actually slowing down, right? Because we're told that it has a constant acceleration of minus 4a, so minus means that, as the diagram suggests, the acceleration or the deceleration of particle 1 is pointing to the left, whereas the velocity, the initial velocity, is pointing to the right. The velocity of the first particle as a function of time can be written as v01, so that's the initial velocity, plus the acceleration of particle 1 multiplied by the time, like this. So if we put in the things that we know, we have the initial velocity to be 4v0, the acceleration is negative, so it's going to be minus 4at, like this. Okay, so this is how the velocity of this particle will change with time, and eventually it will become 0, and then it will change direction. But let's also find the velocity of the second particle, which is traveling in the vertical direction. So let's say that point O is here, and then after some time the second particle is has moved some amount, and it will have a velocity which is going to be given as v2 of t, using the same principle as for particle 1. This is going to be 3v0 plus 3a multiplied by t. Okay, right, so what's going to happen is the velocity of particle 2 will always keep increasing, whereas the velocity of particle 1 will first decrease then it will become 0, and then it will start increasing in the other direction. So let's try to figure out what is the expression for relative velocity. And the way I'll do it, and you don't have to do it this way, but I'm going to look at the velocity of particle 2 relative to particle 1. And I'm going to use vectors for now. So from a vectorial perspective, the velocity of 2 with respect to 1 is just the velocity of particle 2 minus the velocity of particle 1. Now, those two vectors have different directions, right? They're at 90 degrees relative to each other. So I think it's easier for someone who's in 9th grade to actually draw out what will be the triangle. So let's start with the velocity of particle 2, which is this. So I'm going to call this v2. Then we have the velocity of particle 1, which is like this, right? And the relative velocity, which we expressed in vector form as v2 minus v1. So if you consider v1 and v2 to be vectors, which they are, then this direction of the relative velocity can be easily found using triangle rule, and it will look like this. So this green arrow is the vector, which gives us the velocity of particle 2 with respect to particle 1. So if we don't use vectors, which we eventually have to do anyway, it's just how you get to that point, we can actually see that finding this is basically finding the hypotenuse in this right triangle, right? Because those two velocities are perpendicular to each other. So finding the two velocities, v2 with respect to 1, this is square root of v1 squared plus v2 squared. Pretty straightforward. So let's expand this a bit. So this is the square root of. Now v1 is this. So now we just have to plug in the values. So 4v0 minus 4at plus, and this is 3v0 plus 3at. And this should be squared here and here. Okay, so we can now expand the brackets. So this is going to be 16 v0 squared, and then I think we have minus 32 v0 at plus 16a squared t squared. And actually, I think I should have managed my space a bit better. So let's add the second bracket that we also expand. So this is 9v0 squared plus, so this is 6 times 3, so that's 18 v0 at, and then plus 9a squared t squared. Okay, so the velocity, the relative velocity with respect to time is, so we can add 16 and 9 and we get 25 v0 squared. Then we have minus 32 with 18 and we have minus 14 v0 at, and finally we have again 16, yeah, this is supposed to be 6 here. We have 16 and 9, which gives us 25 again, so 25a squared t squared. Okay, that looks nice. So the question is asking us at what time, well, it's asking us two things, right? So it's asking us to find the time first when the relative velocity is minimal, and to find the value of this relative of this minimum relative velocity itself. So the first step would be to, or the easiest way to do it is to first find the time. So you can do this in a few ways, but whichever way you do it, you should first take note that all you need to care about is this quantity under the square root. The square root itself doesn't really matter when we find the time. It will matter when we find the velocity because we'll have to square root. But let's have a look at this, all this stuff under the square root, and let's call that f of t. as in a function of time, right? So let's say f of t is equal to, and I'm going to rewrite the stuff under the square root, but starting from the last term. And hopefully it will be obvious why I'm doing that. So 14 v0 at, and the last one is plus 25 v0 squared. I think that's all. Yeah. So I'm sure people have noticed that this is a quadratic equation, right? We have t squared and t, and we have to find the minimum. So you can do this in a few ways. You can either differentiate, or if you don't want to differentiate, you can also use the fact that the value of t, let's call it t star, right, which gives us the minimum value, is based on the formula that is minus b over 2a, right, from the quadratic equation where we have ax squared plus bx plus c. So a and b are the coefficients of the first and second term. So this will be minus, b is going to be minus 14 v0a, and then on the bottom we have 2 times 25a squared, and this is 14 v0a over 50a squared, and we can cancel out an a, so we get that t star is 14 over 50 v0 by a, or we can say 7 over 25 v0 over a. Right, so this is the time that gives us the minimum, right? And we know this is a minimum because this first term of the quadratic is positive. So if a is positive, then our parabola has a minimum given by this formula, which gives us basically this. Okay, so we found the time. That's great. Now we can plug in the time and get the relative velocity, which is simply found by plugging in the value of time that we got into this. So this is 25 v0 squared minus 14 v0, and then we have acceleration, we have time, so 7 over 25 v0 by a, and then we have plus 25 a squared, and then we have the time squared, which is 49 over 625 v0 over a. I think I missed a square. Yeah, so this should be squared and squared. Okay, right, now we can cancel out a couple of things. So those accelerations go, those accelerations go. This 25 cancels with 625, and we're left with a 25 here. And if you plug in all the values, this should become, if I'm not mistaken, 576 over 25 v0 squared, which you can square root this quite nicely, and this becomes v0 times this is 24 over 5, and this should be it. So this value of velocity is the minimum relative velocity between the objects, and it happens at this time, 7 over 25 v0 over a. And actually we can take this a bit further to have a quick look at the velocities of the two objects at that point. So we've got that the velocity of the first object at time t star is 4v0 minus 4a times 7 over 25 v0 over a, and this becomes, so the a's cancel, we can factorize 4v0, so 4v0 times 1 minus 7 over 25, which is 4v0, and this is 18 over 25. Which is positive, so this means that the first object is still, it's slowing down and is still moving to the right, whereas the velocity of the second object is 3v0 plus 3a times this time that we got here, which is 3v0 times 1 plus 7 over 25. So that's 3v0, 25 plus 7, that should be 32 over 25. So yeah, that's it. We didn't really have to do this part. I was just curious what was the velocity of this first object specifically, or whether the first object started going back, but it turns out that at that point the first object is still traveling in the positive x direction. And that's the end of the question.